Hey everyone, it's been a while since we met. Hopefully you're ready to get back to work here. So before I get started with the notes, just a little bit on what's going on. As far as the notes go, I'm going to be uploading 3 things each day, which seems like kind of a pain, but I wanted to give you options for how you want to take the notes. So I will upload a blank copy of the note sheet so that if you want to print it out and then work along with me while I'm talking through the notes, that's an option for you. I will also upload a completed version of the notes. So if you just want to watch the video and then print out a copy of the completed notes to have, that works. If you just want to watch the video and take notes on your own sheet of paper because you don't have printing capabilities, that would be fine too. And if you don't want to do anything in terms of writing, you'll have access to the notes. So it's really up to you on how you want to handle it. But you will see a blank copy of the note sheet, a completed copy of the note sheet, and then obviously this video to supplement both of those. I know it's not the same as being in class, so if you have questions, you won't be able to ask outright, but by all means email me if there's something that you're not sure about. And then after I'm finished uploading the 3 versions of the notes, I will also upload a practice assignment. The practice assignments will look just like they did before. And again, you can print it and work it out, or you can just work it out on a separate sheet of paper. And then during this 2-week suspension, you're not required to turn in any of the practices that go along with the notes. Now, once the 2-week suspension is over, you will be required to turn in the practice assignments, and we'll talk more about how you're going to do that once we get to that date. So for now, we're going to start in a little bit of a different order than was originally planned for this semester. What we're going to look at are those additional topics that were at the end of our original calendar. So today we're looking at systems of equations, and then we're going to include some applications, which just means toward the end here we're going to see some word problems. But a system of equations means you're looking at not just one equation, one variable, but possibly 2 equations, 2 variables, or 3 equations, 3 variables. So basically, anytime you're looking at 2 or more equations together, we're going to call that a system. So for each variable in your system, there's going to be an equation, or vice versa. So if you have 2 equations in your system, you're going to need 2 variables. Or if you have 3 equations, you're going to need 3 variables, or again, vice versa. And when you're talking about the solution to a system, the solution to your system contains a solution for each of those variables in that system. And if it is indeed a solution to your system, then if you plugged in the value for each of the variables into each of the equations, it's going to make all of those equations true when you plug in. Now, most systems that we encounter are going to be what we call consistent systems. If the system is consistent, that means it's got a distinct solution, or if it was a possibility of having multiple distinct solutions, it's consistent. And if you have a system that has no solutions means it's going to be an inconsistent system. And let's try that again. So consistent means you're going to have a distinct solution. Inconsistent means no solution. Now, it is possible that your system contains equations that are exactly the same, in which case you would have an infinite number of solutions, and we're going to call that a dependent system. And I'm going to show you how each of these things can occur. It's easiest to see it when we focus on what we call linear systems. So we know what a linear equation is. A linear equation is your y equals mx plus b format. So remember from our parent function unit, if we have something like y equals mx plus b, that's the slope-intercept form for a linear equation. If it's a linear system, that means your equations in your system are all linear functions. And if you're looking for the solution to a linear system, since your linear system, your variables are going to be just an x and a y, it's that x and y value together are going to represent the point where your lines are going to cross. So the solution to a linear system is the point where the 2 lines would cross, because again, it contains the value of x and y that make both of those equations true. So what you see in the first picture here is a consistent system. If you were to graph 2 lines, majority of the time, those 2 lines are going to cross at one distinct point, and this one distinct point happens to be the solution. So this would be the solution. That is the value for x and y that would make both of those equations true. So most of your systems are going to be consistent. They're going to have that one solution. Now, if your system is inconsistent, inconsistent means no solution. If there's no solution, it's because there's no point where your lines are crossing, and that would happen here, as you see with parallel lines. If your two lines are parallel, there's no way they're going to cross. There's no way you're going to get a solution. Now, if you were to graph two of the exact same equation at the same time, so you can see I have y equals -2, or negative 2x plus 3 there, and then you have it again here. I graphed it twice, but you can't see two lines there because they're the exact same line. Now, technically, if you graph them twice, one just ends up right on top of the other, which means that those two lines would be touching each other at every single point. That would be an infinite number of solutions indicated, and that's, again, what we call a dependent system. So this would be infinite solutions, and that's because we have the same equation twice. Okay, so now these other two here, the parallel lines or the same equation twice thing, these are the special cases. The majority of the time, that's not what's happening. Majority of the time, you're going to have a consistent system. You're going to have two lines that cross exactly once. Now, I need to back up here because I forgot to mention something here. So your system, again, multiple equations, multiple variables at the same time. If it's two equations and two variables, we call that a 2-by-2 system. And that's really going to be the focus of the notes today. Although tomorrow, we're going to look at something a little more complex. So if you have three equations, three variables, we're going to call that a 3-by-3 system. And if you had four equations, four variables, a 4-by-4 system, and so on. Okay, so the focus today is these 2-by-2 systems, which we just saw could be consistent, containing one solution, inconsistent, containing no solutions, or they could be dependent, meaning infinite solutions are possible. Now, if you actually want to find the solution to our consistent system, or if it's a special case, I'll show you how to deal with those too. There are a couple of ways to do this algebraically, and one of those ways is called substitution. If you're solving algebraically using substitution, this method is going to be preferred when at least one of the variables is alone. For example here, if we were looking at this system, 3x minus y equals -10, and y equals 6 minus x, because we have y all by itself in this second equation, we can substitute in what y is equal to the first equation, which sounds a little complicated, but here it is. So if y is equal to 6 minus x, that means the 6 minus x can replace y in the other equation. Because y and 6 minus x are the same, then anywhere I see a y, I can replace it with 6 minus x. So I can rewrite this first equation where the 3x doesn't change, the minus doesn't change, but instead of a y, I can substitute in what y is equal to, which we just said was 6 minus x, and then I still have the equal, and I still have the minus 10. Now what that does is it creates one equation, one variable, and that's something that we know how to solve, right? Two equations, two variables at the same time does us no good. But now with one equation, one variable, we can solve for the one variable that's left. So if I distribute the negative here, let's see, the negative goes here and here, and we're looking at 3x and then a minus 6 and a positive x, still equal to -10. Combining like terms, the 3 and the 1 gives me 4x here. If I add the 6 to both sides, a couple steps at once here, adding the 6 to both sides, that gives me 4x equal to the -10 and positive 6 makes a -4. And now I can divide both sides by 4. And now I have x by itself equal to -4 divided by 4 makes a -1. Now, if all we were solving was that one equation with one variable, all we would need is that one solution for x, we'd be done. But here we're actually looking for the solution to the whole system. So we're looking for a value of x and a value for y. That way we have the whole coordinate where these two lines would be crossing. So once we have the value for the first variable, we're going to plug in that variable into either equation to find the one that's missing. So I think the easier equation to plug in here is going to be the second equation. So if we use our second equation, it says y is equal to 6 minus x. Well, we just found x was -1. So in place of the x, I'm going to plug in a -1. So that means y is equal to 6 plus 1, which means y is equal to 7. So if x is equal to -1 and y is equal to 7, that means if I was to graph these two lines, they would cross at -1, positive 7. So that is the solution to this system. That is the x value and the y value that would make both of those equations true. and that is the point where those two lines would cross. Okay, now I wouldn't do this every time, but if you absolutely wanted to be sure that you were doing this correctly, you could check, where you would plug the -1 in for x, plug the 7 in for y into both of those equations and make sure both are true. So let's see, 3 times -1 minus 7 should be equal to -10. So that's -3 minus 7, and that's true. -10 does equal -10. So it works for the first one. Now I'm just going to verify with the second one. So the second one, y, which is 7, should be equal to 6 minus x, which is a -1. That's 7 equal to 6 plus 1, and 7 does equal 7. So there's a way for you to algebraically solve and verify your work. Okay, let's try that again. So this time, again, this method of substitution works really well when you have a variable all by itself. So this time x is all by itself. So in this case, if we know that x is equal to 3y minus 4, then we can replace x in the other equation with 3y minus 4. So we have 4 times instead of x, we're plugging in 3y minus 4, and then we still have a minus 5y and an equals and a -2. So distributing here, we get 12y minus 16. I'm going to bring down the rest. And then I can combine these like terms. So 12y and -5y is going to give us 7y. Oops, let me go back to blue here. So that gives me 7y, and then I'm going to go ahead and add this 16 over. Add the 16 over, so now I have 7y equal to -2 and positive 16 makes 14. Now I can divide and be halfway to my answer. So dividing both sides by 7, we see that y has to equal 2. Now remember, that's only half of our answer. We need the x value, so we're going to take that y value and we're going to plug it in. Now it doesn't matter which equation you plug into, but if we're trying to solve for x, it makes a little more sense to use the first equation. So the first equation says x, which we're trying to solve for, is going to equal 3 times y, so 3 times 2 minus 4. So that's going to be 6 minus 4, and 6 minus 4 is 2. So if I was to graph these two lines, I would see them cross at the point 2, 2. X is 2, y equals 2. And again, if you want, you can plug 2 in for x, 2 in for y into both those equations, and it's going to make both of them true. Okay, so there's one here for you to try. I'm going to go ahead and work through it, and feel free to try and then compare your work. All right, anyone else get stuck here? So if y is equal to 2x minus 4, replace the y with 2x minus 4. And when you distribute the 3 to the 2x minus 4, you end up with 6x minus 12. And at this point where I'm at here, when you try to combine the 6x and the other -6x, what happens is the variables cancel. So what we're left with here is -12 equal to 24. No variables left. Any ideas on what that means? I'm picturing myself looking at a classroom of students. So obviously no one's got an answer for me. What this means is we have one of our special cases. If the variables cancel, it's going to be one of those cases where you either have no solution or you have infinitely many solutions. And the way you're going to know is based on the statement that's left over. So if your variables cancel, to determine if it's a no solution or an infinite solution, you got to see if the statement that's left is true or false. So when you're looking at -12 equals 24, is there any way for -12 to ever equal 24? Absolutely not. So since these two things cannot be equal, that statement is false. That false statement that's left over tells you that there is no solution to this system. There is no solution to this system, or you could also say that the system is inconsistent. Really, either one of those would be perfectly fine for an answer. So it's when the variables cancel that you're going to see this happen. Now, I can show you why. If you were to take this second equation here and solve it for y so that it looks like the other one here. So if you had 3y and you added over the 6x, you'd have 6x minus 24 on this side. If you divided everything by 3, you'd have y equals 2x and then minus 8. Now notice in the first equation, the slope is 2. And in this equation, the slope is 2. If those slopes are the same, that means these lines are rising and running at the same rate. So if they have the same slope, they're rising and running at the same rate, they're going to be parallel. Now because this one crosses at -4 and this one crosses at -8, that means that they're not crossing the y-axis at the same spot, right? One is shifted up a little higher than the other. So one starts at -4, one starts at -8, but they're rising and running at the same spot. They're parallel lines. So that's why this is an inconsistent system. There's no way that these two lines could ever cross. Okay, so let me get rid of some of this work. Erase. All right, so because these lines are parallel, they're never going to cross. Now I'm going to have to fix this. Give me 1 second here. So this all went here. But the note that I want you to keep in mind for yourself is when the variables cancel, a false statement, okay, can't fit that in there, a false statement remaining implies this, no solution. Okay? So then you would know what would happen if the variables canceled and you got a true statement. That would imply you'd have a dependent system. That means you would have exactly the same equation twice and they would cross it at every single point. Okay? So substitution, really handy if you have a variable that's all by itself. Now sometimes that's not the case. So for example here, none of these variables is alone. If I wanted to use substitution, I'd have to either get the first or x or first y or second x or second y alone. And let's say I wanted to get the first x by itself. I have to add the 6y, divide the 3. It would take a bunch of work. And it would take the same amount of work for any of those variables to be alone, which is possible, right? If I wanted to solve for y in one of the equations and then plug in, or solve for x and then plug in, I could absolutely do that. But these equations are in what we call standard form. And if they're both in standard form, where your x's are aligned here, y's are aligned, and the constants are aligned, then we're going to want to use another method called elimination. So if you're solving algebraically, the elimination method is going to be preferred when the equations are in, as I mentioned, standard form. So versus the y equals mx plus b, or having a variable alone. So standard form is when you have the x term, and then the y term, and then you have the constant. And that's what we have here. We've got the x terms all lined up, y terms lined up, constants lined up. Okay? So when that's the case, we're going to try this elimination method. And what happens with elimination is, or what you can do with elimination is you can add the equations together to eliminate a variable. So for example here, if we just added these equations together, so I'm going to draw a line underneath these equations here. If we just add them together, what happens when you add 3x and 5x? Well, 3x plus 5x makes 8x. And then what happens when you add negative 6y and positive 6y? Well, they cancel. So those are gone. And then we have our equal sign. And then 21 and 3 makes 24. So adding these equations together leaves us with one equation, one variable. And now if I solve this one equation with this one variable by dividing both sides by 8, then just like before, I get half of my solution. So I know the x value for this system has to be 3, and then I got to plug it in to find the y value. So either one, I'm just going to choose. I don't think either one is easier than the other to plug in. I'm just going to choose the first equation. If I plug the 3 in, so 3 times x, or 3 minus 6y, has to equal 21. That's going to be 9 minus 6y equals 21. I'm going to subtract the 9 from both sides. So I have negative 6y equal to 12. And then I'm going to divide both sides by negative 6. And those will cancel. And that leaves me y equal to a negative 2. And there it is. Okay, if I was to graph these two lines, they would cross at 3 and negative 2. Okay, so I know it looks like a little bit of witchcraft if you've never seen elimination before. And I could try to explain it, but it's a little hard here to try to cram all this in already. But adding the equations together is a perfectly legal move, and that is the goal with elimination. Now, this example I showed you was really set up perfectly for elimination because the variables canceled right away, but that's not always the case. So for example, in number 2, if you try to add the equations together as is, the 5x and 3y, they don't cancel. That's not really helpful. So in a case like this, we still want to use elimination. Actually, you could use substitution if you wanted to get this y by itself by just subtracting the 2x over and then substitute in, you absolutely could. But if you want to use elimination, because they're in standard form, you're just going to have to multiply one of your equations first. So you pick a variable to get rid of. I'm going to pick the y's to eliminate. If I want to eliminate the y's, what I need is for their coefficients, so the number in front here and the number in front here, I need those coefficients to be the same number with opposite signs. So what we're looking for is the least common multiple for 1 and 2. It's like when you're finding a least common denominator, right? If you had denominators of 1 and 2, what would the least common denominator be? It'd be 2. So least common multiple for 1 and 2 is 2. So what I want is to make the coefficients a positive 2 and a negative 2, which is good news because I already have a positive 2 in front of the second y there. Now if I want to make the first equation, if I want the coefficient here to also be a negative 2, then I have to multiply not just the y, but the whole equation by negative 2. As long as we multiply the whole equation, we're not changing the value, we're keeping the balance in that equation. So I'm going to take this whole first equation and multiply by negative 2. So my first equation, 3x plus 2y plus 2y equals 1, not changing. But the second equation becomes a negative 4x and a negative 2y. And a negative times a negative makes a positive 4 there. And so that's the exact same equation, but because it's now multiplied by negative 2, when I add these equations together, my y's will cancel. So 3 and negative 4 leaves me a negative 1 in front of x, and then 1 and 4 leaves me 5. So now if I divide both sides by negative 1, those negatives cancel, and I have half of my solution. I have x equal to negative 5. And then you pick an equation to plug into. I'm just going to choose this first one. So we have 2 times x, which we found was negative 5, plus some y value we still have to find equal to negative 2. So that's negative 10. And if we add that 10 over, plus 10, those will cancel. And we can see that y is equal to negative 2 and 10 makes 8. So if I was to graph these two lines, they're going to cross at negative 5 and 8. Okay, so there's one for you to try here. Go ahead and give it a go while I work through it. So the first equation the second equation I just brought down. The first equation, multiplying by 7, 7 and 7 gives me 14x negative 7y, and that's not helpful. Gonna have to multiply by a negative 7. Hopefully you can see why that needs to be the case. So the first equation not changing. The second equation not changing. The first one, if I multiply by a negative 7, that's going to make a negative 14x in front here, which could make those cancel. It also makes a positive 7y here, which makes those cancel. And then it makes a positive 21 on the other side. So multiplying that whole first equation by negative 7 makes everything cancel, which means technically we're left with 0 on this side of the equal sign, and technically left with 0 on the other side of the equal sign. And when the variables cancel again, that's when you have one of your special cases. But this time, notice, 0 is equal to 0. That means these two equations are exactly the same equation. It's the same equation twice. One's just a multiple of the other. If you were to graph these two lines, they're going to cross at exactly the same point. And so we have, again, what we call a dependent system. So this statement, this true statement, implies we have infinite solutions, an infinite number of solutions. Or we could say infinitely many solutions. Infinitely many solutions would be a good answer there. Or if you wanted to say that this is a dependent system, that would be an acceptable answer as well. And again, when your variables cancel and the statement that's left over is true, that's what you have. So when variables cancel, and the remaining statement is true, then you have infinitely many solutions, or a dependent system every time. Okay? All right, I know I'm talking a lot here, but we're getting there. Oh yeah, we're getting there. Okay, so solving by graphing is going to be another option, and actually I think this is the most intuitive option. All of these systems that we're looking at, these linear systems, we're looking for the point where the lines cross. So I think the most intuitive way to find the point where the lines cross is absolutely to graph. And it's not always preferred. Like I like to work out things algebraically, and when we get to some of the more complicated systems, you're going to have to know how to use substitution and elimination. But sometimes your systems just are going to be ugly to solve by hand. And in either case, whatever the case may be, graphing is going to be a great way to find the point where two lines are crossing. So the goal is to graph each equation and find the intersection. Find where your two lines are intersecting. That's going to be your solution. And obviously, you can use whatever means of graphing that you want, but you know what I prefer, and that is Desmos. Okay, so I'm just going to try to show you here. See if I can get Desmos on my screen at the same time. There we go. So I'm going to type in my first equation, which is 2x plus y equals -5. Type in my second equation, x minus 3y equals -13. And you can see your two lines are graphed here. Two lines are crossing at -4, 3. If you just tap on the point, it's given there for you. That is the solution to the system. And all of the previous ones that we did by hand can be done the same way. Okay, you can, this is a nice feature about Desmos. When you're graphing in your calculator, it's got to be in y equals to graph. When you're graphing in Desmos, you don't have to manipulate your equations. You type them in as is, and they'll graph for you. So we typed them in, we see where they graph, boom, we have the solution again. All of the previous problems we've done can be done the same way. So there'd be another good way for you to verify your work. So the solution here is going to be -4 and 3. And let's see if I can get this one in. So the second one we have, this is absolutely not something that I would want to solve by hand. Okay. Can I move my calculator? There we go. So I wouldn't want to mess with those decimals, although you absolutely could try to solve by hand. Desmos is a great alternative. So we have 0.75x minus 1.5, and then -0.2, oops, forgot my y equals. Y equals -0.2x plus 4.8. And there it is. Not a nice solution. Makes sense. We had a bunch of decimals in our equations. So at 6.632, comma, let's see, 3.474, we have our solution to that system. Okay? All right, go away, Desmos. No? All right, bear with me here. My technology. It's gonna work. No. Anybody else know how to do this? Too bad nobody's here to help me. Okay, finally. All right, so that's linear systems, solving by substitution, elimination, graphing. I know we're getting pretty lengthy on time here. I'm sorry we got to cram so much in. But I'm going to show you some applications. These are just some examples of word problems where you could apply the same process. So the hard thing about word problems, we know, is not one way to do everything, but you definitely want to read through your problem. And in these problems, we're going to be looking at multiple variables because we've got multiple equations, so define your variables. And then you're going to try to write a system that models your situation. I'm going to work through hopefully some examples to get you going. And then you're going to solve using substitution, elimination, or graphing. And I would probably lean toward the graphing or Desmos just because it's the fastest and most efficient. And then once you've solved, just make sure that you have an answer that makes sense for your problem. Okay? So each problem is going to be a little different. You're going to want to write a system that models the information that you're given, okay? So Tyrell bought 4 pens, 5 pencils for $6.71. Dana bought 5 pens and 3 pencils for $7.12. We're trying to find the cost for 1 pen and 1 pencil. So I'm going to call pens X and pencils Y. Those are our 2 variables here. And what they're giving us is information for Tyrell and what he bought, and then information for Dana and what she bought. So I'm going to start with Tyrell. So it says for Tyrell that he bought 4 pens and 5 pencils for $6.71. 4 pens would be 4 X's and would be plus 5 pencils, 5 Y's, for a total of, so that's equal to, $6.71. And hopefully that's a reasonable setup for you there. Okay. Secondly, it says that Dana bought some things here. So I'm going to make a second equation for Dana. It says that she bought 5 pens and 3 pencils for $7.12. So 5 pens and 3 pencils for $7.12. And there you have it, your system. Now, if I was solving this by hand, I think this is set up perfectly for elimination. But because we have technology, we're going to go ahead and let Desmos do the heavy lifting for us here. All that work trying to get the calculator to go away just to bring it back. Okay, so we've got 4x plus 5y equal to 6.71. Make sure you get the decimal in there. Okay, and then we have 5x plus 3y equal to 7.12. Okay, so we've got our system. I'm just going to zoom in to make sure I'm actually getting the intersection there. So these are intersecting at 1.19 and 0.39. Now, if this system had no context, we'd leave the equation written as an ordered pair. But since the 1.19 and 0.39 represent something here, we want to put this in an answer that makes sense. So X represented pens and Y represented pencils. That means we could say pens cost $1.19 and pencils cost 39 cents. And there it is. Okay, not so terrible. All right. Not so terrible because we always like to put the easy ones first. Okay, so let's try this again. This time we have a piggy bank full of dimes and nickels. I don't know why you would have a piggy bank full of dimes and nickels, but this actually happens in my house, my side story. My son, he doesn't like pennies, so he never puts pennies in his piggy bank. He always puts them in his brother's. And then we have this water dispenser that we use. We get the 5-gallon jugs. We fill them up with the water machines, like in front of Walgreens or Fry's. And it takes quarters. So I'm always robbing him of his quarters. So he gets rid of his pennies. I take his quarters. His piggy bank is full of dimes and nickels. Anyway, sorry, side story. So there's 140 coins total, and $11.30 is the total value. And our job is to figure out how many dimes there are. So how many dimes there are, let's call them D for dimes. Even though that's the only variable they're asking for, there are actually 2 variables here. We don't know how many dimes there are. We also don't know how many nickels there are. So I'm going to call those N. Okay? So what we have to do is write 2 equations, again, for what we're given. Like in the last example, we were given information about Tyrell and Dana. Here we're given information about the total number of coins. So I'm going to write 1 for the total number of coins. Total number of coins. Okay, so if there's 140 coins total, I don't know how many dimes there are, and I don't know how many nickels there are, but if I add the number of dimes and nickels, I'm going to get 140 coins. Okay, so there's one equation. Now we have to have another for the value of the coins. 1 for the value of the coins, because that's what they're giving us, right? They're giving us, there's total number of coins, and they're giving us the value. So it's 10 cents for every dime. 10 cents for every dime, plus 5 cents for every nickel, and altogether $11.30 for that total value. Okay, so again, I think this system is set up for elimination if you were going to solve by hand, but there's just no need for us to do that work by hand when we have Desmos. So we're going to let the calculator do this for us again. We have, in here we have to use X and Y, but we'll get the same results. So let's see, 0.1x plus 0.05y and 11.3. All right, not showing up on my screen here. Just gonna zoom out and see. Oh, there we go. So I'm gonna zoom out there and figure out where we were headed. What did I do wrong here? Oh, forgot my decimal point. You understand why I'm looking at this graph knowing it's wrong? So I knew I made a mistake typing something in because I had negative in that value, and I had decimals. Decimal answers wouldn't make sense. I'm not going to have a decimal amount of dimes or nickels, and I definitely shouldn't have anything negative. So I went back to my equations and realized I missed a decimal point here. So now we should be looking at something more reasonable, and yeah, that makes a lot more sense. So these are intersecting at 86 and 54, where the x was the first variable that was dimes, and the second variable y we called n. So we have 86 dimes and 54 nickels. And that definitely makes 140 coins, and I can guarantee if you multiply 86 dimes times 10 cents each and 54 nickels times 5 cents each, you'd get a total of $11.30. Okay, so almost there, guys, almost there. Hang on with me. All right, so this is probably the tougher one. Metallurgist, I don't know if you've ever heard that word, but basically someone who works with metal, needs to make 15 milligrams of an alloy that contains a 65% iron. So he's going to melt and combine. He's going to melt and combine one metal that is 5% iron with another that is 80% iron, and how much of each should he use? That is a lot of information going on. So he's trying to get a 65% iron. He has an iron on hand that's only 5%. He's got another one on hand that's 80%. So he's trying to mix this low-end one with this high-end one to get something that's kind of in the middle. Okay, so we have to figure out how much of the 5% iron, let's call that X, and how much of the 80% iron, let's call that Y. How much of those things does he have to mix together to get this mixture, okay? So now the tough part, how do we get these two equations? Well, he needs to make 15 milligrams all together. That's the total milligrams of alloy that he needs. So we're going to make one equation for the total number of milligrams. So I don't know how many milligrams of the 5% iron, and I don't know how many milligrams of the 80% iron, but together, 15 milligrams altogether. Okay? Now, I also know that this mixture has to be 65% iron. So what I want to do in the next equation is attach the percents to all of these amounts. So we're going to use the percents per amount in this next equation. So the X amount of 5% iron, right, it's going to be 5%, that's 0.05 for every milligram of that X amount. Plus we're looking at an 80% iron here, so 80% per milligram of that particular iron. And then the last part here is what's really tricky. So we attach the 5% to X, the 80% to Y. We also have to attach the 65% to the 15 milligram total here. So it's 65% per each of these 15 milligrams. So one equation for the total number of milligrams, and then one that attaches the percent to each of those amounts. So the percent times X, the percent times Y, and the percent times the 15 total. And that was the tough part. Now that we have the system, which could be solved by hand using elimination, we're going to go to Desmos, because I'm not trying to deal with all those decimals. All right, so we have x plus y equal to 15. What did I do? Equal to 15. And then we have 0.05x plus 0.80y equal to 0.65 times 15. And now we gotta figure out where our lines are. All right, so scrolling around, there we have our intersection. So these are intersecting at 3 and 12. And get rid of that. So 3 and 12, again, this was your x and this was your y. So that means we had 3 milligrams of x, which was the 5% iron. And then we have 12 milligrams of the y, which is the 80% iron. Okay, definitely not the easiest, but let's look at another that sort of works the same way, okay? How many liters of a 50% saline solution must be mixed with 2 liters of an 80% solution to make a 60% saline solution? Mouthful even to read. Okay, so let's look at what's happening here. We're mixing together 50% solution and an 80% solution to get a 60% solution. So again, there's a lower end, there's a higher end, and we're trying to make a mixture that's somewhere in the middle. So how many liters of a 60 or a 50% solution, don't know, let's call it X, is going to be mixed with 2 liters of the 80% solution? That's not a variable there. We know exactly how much of that is going to be, and that's going to be making a 60% solution. I don't know how much of that there's going to be. So how many liters of a 50%? I don't know. Is going to be mixed with 2 liters of an 80%. We know how much of that we're using to make a 60% solution, and we don't know how much of the 60% solution there is. Okay? So one equation is going to be for the total number of liters, like we had on the other one. Total number of milligrams is now total number of liters. Okay? So it's going to be X liters of the 50% plus 2 liters of the 80% to make Y liters of the 60%. So this is our mixture, right? This is our mixture, and this is what we're trying to get. Okay, so now we're going to take our amounts and attach the percent. So this is the percent per liter. So the X represents the 50% solution. So 50% per liter here, plus the 2 liters was 80%. So 80% per liter per 2 liters here. And then the Y, what we're trying to get there is a 60% solution. So 60% times Y here. Okay, so that was the tough part. Now we let Desmos do the heavy lifting. And, okay, guess we'll deal with the split screen. So, X this time plus 2 equal to Y. And then here, 0.5x plus 0.8 times 2 equal to 0.6y. And we have in here a solution at 4 and 6. Make that go away. Okay, so if they were intersecting at 4 and 6, this was x and y. So we are mixing 4 liters of the 50% solution. Sorry about that. Of the 50% saline with the 2 liters of 80% to get to the 6 liter total 60% solution. And there it is. As if that was simple. Okay? Lucky for you, you can pause and rewatch. And again, feel free to email me if you have any questions. In a little while, I will get this uploaded along with the blank versions, and then I'll also upload a practice assignment for you. Please, please, please try to keep up with your work and email me if you have any questions.